morning class. Today we will going to study corrosion in materials. Our focus while studying corrosion will be on corrosions happening in metals. In this particular unit, we will going to discuss the science behind corrosion, the causes of corrosion, different types of corrosion, and at last we will discuss methods by which you can prevent corrosion in metals. So at the end of this unit, every student will be able to propose a solution to prevent corrosion in metals. So the first question is, what exactly the corrosion is? Corrosion is the deterioration and loss of metal or material by chemical or electrochemical reaction within a given environment. It is a natural and universal process. Every material exists on universe undergoes corrosion. The only difference is the degree at which the corrosion takes place in different material is different. Most of the metallic elements except noble metals, which are in the extreme stable state, undergoes oxidation, and this causes corrosion in metals. The scientific reason behind materials undergoing corrosion is the material's tendency to reduce the energy of the system, which the materials achieve by undergoing the corrosion. That means the internal energy of the system is higher and the internal energy of the corrosion byproduct is lower. Hence, material tends to corrode to minimize its internal energy. In general, metals gets oxidized, polymers reacts with the oxygen and gets degraded, while ceramic melt themselves into the material in which they are in contact. These are the primary modes by which different class of materials gets themselves corrode. The most common version of the corrosion that we are exposed to is the formation of rust on the iron and copper surfaces. When iron gets corrode, it forms this red color iron hydroxide, while the copper forms a fine layer of green colored copper hydroxide surface. Corrosion is mainly dependent on the metal's own characteristic, the environmental circumstances, the temperature and the pressure, and the design of the material itself. How the design plays a role in corrosion, we will discuss it at a later stage. Corrosion in metals is basically an electrochemical process. So every time when you discuss corrosion in metal, it is in fact an electrochemical reaction which the material is undergoing. You people have studied the electrochemical reaction in your +2. It is basically an oxidation reduction reaction. We know that metals have tendency to liberate electron, and in this process they get oxidized. For example, if you have iron, then iron generally liberates 2 electrons and gets converted into a ferrous iron, which is Fe2+. And likewise, aluminium can liberate 3 electrons and gets converted into Al3+. In this process, the metal gets oxidized. Now, the liberated electrons moves to the other species, which accepts these electrons and undergoes a reduction reaction. The examples of the reduction reaction is H plus ion accepts the incoming electrons and gets converted into a hydrogen molecule. Since the reaction takes place in the H plus environment, it is basically the acidic environment. Likewise, H plus ions can also accept electrons in the presence of dissolved oxygen, and your final product will be water. This reaction is also taking place under acidic environment. Similarly, water can accept incoming electrons in the presence of oxygen, and it produces hydroxyl anions, which makes the overall solution basic. Now, a given material undergoes corrosion by electrochemical reaction. Out of the two different metal junction, which one will going to corrode more? That depends on its electrode potential. Electrode potential is basically the voltage which is being produced when two different metals are in physical contact with each other, which is being placed in an electrolyte. So to understand how exactly the electrode potential is being measured, you need to look at the schematic diagram of a galvanic cell. Galvanic cell is basically a structure which looks like this, in which we take a glass cell having two compartments. In each of these compartments, you put two dissimilar metals. In this example problem, on the left hand compartment, we have a piece of iron, while on the right hand side, I have a piece of copper. These two are electrically connected through a voltmeter. Both these plates are put in a compartment which is filled with corresponding ion solution. Here, Fe2 plus solution of 1 molar strength is being kept, while on the other side, Cu2 plus solution of 1 molar strength is being kept. Each half of this galvanic cell is referred as standard half cell. Now, if you have one standard half cell and on the other side, if you have a hydrogen electrode, then the corresponding voltage which is being produced is referred as the electrode potential for that particular metal. In this case, the iron liberates two electrons, and in this process it gets dissolved into Fe2 plus, which goes into the solution phase, while the liberated electron travels to the other compartment, interacts with the Cu2 plus ion in the solution phase, reduces it to Cu, which gets deposited on the copper plate. So in this way, iron undergoes an oxidation while Cu2 plus undergoes a reduction. Therefore, in this case, Fe acts as an anode while Cu acts as cathode. Between two metals, which metal will act as an anode and which will act as cathode, that depends on the relative electrode potential of that particular metal piece. This is being described in terms of the standard electrode potentials. A list is being shown in this particular table here. A metal lying higher on this table, that means possessing greater electrode potential, is more noble. That means it is highly unlikely to undergo corrosion. While the metal which lies lower on this table is chemically more active and more prone to undergo a chemical reaction by which it gets corroded. So if you move from top to bottom, your chemical reactivity increases and your possibility of metal undergoing corrosion becomes higher and higher. Remember, amongst any two metal, the one that lies on a higher side in the table will act as cathode, while the one that lies lower on the table will going to act as anode. Likewise, so if I connect iron and copper, then amongst the two, you can see your iron is here and your copper is here. So amongst the two, copper lies on the higher side, so it will act more noble, remains protected, while Fe lies below in the table, will undergo corrosion. So within this junction, Fe gets converted into Fe2 plus, and in this process, it gets converted into FeOH2, which is basically the iron hydroxide, or you can say rust of iron, while copper is acting as cathode, so it remains protected. So in any two dissimilar metals, when in physical contact with each other, the one that undergoes corrosion will act as an anode, while the one which is chemically more inert will act as cathode. Now, two metals which are in physical contact with each other is being referred as the galvanic couple. Now, depending on the position of the two metals on the electrochemical potential series, one will act as an anode while the other one act as cathode, and there is a definite potential difference between the two. For example, if I make an iron copper junction or a zinc iron junction, the difference in their electrode potential is different. For example, between Cu and Fe, your standard electrode potential difference is 0.78 volt, while for iron and zinc, it is 0.323. That means the potential difference between copper and iron is more as compared to between iron and zinc. So amongst the two, the junction of copper with iron is more prone to corrosion as compared to the junction between iron and zinc. Amongst the two metal or any two material, which one will undergo corrosion, that depends on its relative position on galvanic series. Any material that lies higher on the galvanic series will be more inert and hence act as cathode, which remains protected from the corrosion, while the one that lies lower on the galvanic series is increasingly more active and hence act as an anode, which will undergo an oxidation reaction and hence will corrode. Now, there is no standard protocol that a given material will always act either as an anode or as cathode. For example, if I make a junction between silver and copper, then since silver is lying on a higher side on the electrochemical series as compared to copper, silver will going to act as cathode and remains protected, while copper will act as anode and will undergo corrosion. But if you replace silver with, say, cast iron, then since cast iron is now lower on the electrochemical series as compared to copper, therefore now copper becomes a cathode and cast iron will become an anode. So cast iron will now get corroded while the copper remains protected. So always, while deciding an anode and cathode, you have to consider the electrode potential of that particular material on the galvanic series. The material whose corrosion you want to prevent should lie lower on the electrochemical series as compared to your sacrificial material that will eventually corrode. Corrosion is being measured in terms of corrosion penetration rate, which is also called CPR. It is being defined as CPR is equal to Kw upon rho AT, where W is the weight loss of the material after an exposed time T. Rho is the density of the material, A is the area which is exposed to the corrosive environment, and K is your rate constant, or you can say proportionality constant. The reaction penetration rate, or you can say the corrosion rate, is also being measured in terms of the electric current that is being produced in an electrochemical reaction. In terms of the current density, corrosion rate R is being defined as R equal to I over NF, where I is the current density, N is the number of electron associated with the electrochemical reaction. For example, Fe gets converted into Fe2 plus. In that case, N is equal to 2 and F is Faraday's constant. Materials corrosion can be prevented by a process called passivation. Many materials, for example, chromium, iron, nickel, titanium, and their alloys form a thin layer of an adherent surface which prevents the oxidation of these subsequent layers of the material. So formation of a thin oxide layer on the surface of the material which prevents its further oxidation is being referred as passivation. The classic example of prevention of corrosion through passivation can be observed as Ashoka Pillar in Delhi. So, in summary, what we have understood so far is corrosion is due to an electrochemical reaction in metal. The corrosion depends on the environmental conditions. The electrochemical reaction between two different metals give rise to corrosion. The corrosion in galvanic series is more when the potential difference is higher. And passivation is the process by which the chemical reactivity vis-a-vis to corrosion can be minimized. This is all for today's discussion. Tomorrow we will going to discuss different types of corrosion and the ideas with which you can prevent corrosion in metals. Thank you.